Hello, welcome back to free online classes through YouTube channel. Today I'm going to discuss very important topic, that is the basic postulates of quantum mechanics. So before entering this topic, here I'm going to frame a couple of questions. Number one is first question: how a quantum state is described mathematically at a given time? How a quantum state is described mathematically at a given time t. This is my first question. And second question is how to calculate the various physical quantities from this quantum state. Next, third question is, for example, knowing the system state at a given time t, how to find the quantum state at any later time t, and that is how to describe the time evaluation of a system. This is my third question. Knowing the system state at a time t, this is t prime. Okay, this is t, this is t prime. So these are my three questions. First question is the how a quantum state is described mathematically at a given time t. The how to calculate. Second question is how to calculate the various physical quantities from this given quantum state. For example, if you know the system state at a given time t, then how to find the state at any later time. That is how to describe the time evaluation of a system. So the answers to these questions are provided by the set of five postulates. Number one is first postulate. So it's better to write like this. Okay. Postulate one. state of the system. So the state of any physical system is specified at each time by state vector, that is get vector. This is get. So this get vectors are belongs to Hilbert space. Hilbert space H. Okay, or else we can write like this. So this wave function contain all the needed information about the system. Any superposition of a state vector is also a state vector. So this wave function psi is contained. Wave function psi get contain all the needed information about the system, and also any superposition of state vector is also a state vector. In case if you are new this channel, please go and watch. So whatever I written here, these 4 lines, almost I did 6 classes. I mean, number 1, number 2, up to 6. I think these 6 classes I try to define in the classes quantum system. So the quantum state, not a system, the quantum state. I try to define, I try to explain what is quantum state. Okay, in case we don't know the what is quantum state, please go and watch video number 1, 2, 3, 4, 5, 6 up to 6. So then you can understand what is the uh, how quantum state is described in quantum mechanics. So mathematically, how it can be described. So I can explain all these things. So this is the first postulate. Okay. So this wave function is some constraints are there. The 5 constraints. So constraints on side. Some restrictions are there. We cannot pick any one of the wave function. We can describe the quantum system. I mean quantum state of the system. So it is not possible. That is absolutely imaginary topic. So here some uh, restrictions are there by choosing that quantum system or design the function to choosing the function, either it is sin x or cos x or the x square. Some different type of functions are there in mathematical function. Out of that functions, we need to pick up some functions. So some functions are follow the uh, what is required to describe the state of the system in quantum mechanics. So we can pick that quantum systems, I mean quantum functions. So constraints on that wave functions. Constraints on wave function psi. Here is the first constraint. Psi, wave function psi is well defined. And well behaved. Second constraint is wave function must be finite and single value. Third constraint, psi must be continuous. Fourth constraint, first derivative of psi is continuous. Fifth constraint is there must be second derivative for wave function psi. Okay, so this is how we defined the quantum state of the system. Okay, state of the system. So the state vector is belongs to the Hilbert space. So we already discussed this Hilbert space. So simply here I'm going to discuss one more time one bullet word. For example, here one particle is there. This is space x, y, z axis is there. This is x axis, y axis, and z axis are there. So this is the particle. So this origin, this is the particle. For example, okay. So here I need to describe this system. Here I want to 3 degrees of freedom because this is space. So there is no constraint on the system. It can be moved along x-axis, y-axis, z-axis. So we need 3 degrees of freedom to describe the system. Okay, what is the position? In case I want to describe, I want to know the momentum of this system. Momentum of the system. So I need additional 3 more degrees of freedom, right? 3 are the positions. Okay, position, and 3 are the momentums. So in case if you add one more angular momentum, orbital angular momentum like this, so it is keep on increasing number of degrees of freedom. So in case if I choose, I want to know the system, the position and momentum, I need 6 degree of freedom. In case if I add another physical quantity, I need 9 degrees of freedom. In case if I want uh, n physical quantities from this system, need to describe the n degree of freedom. Like that, we can go up to the n degrees of freedom. That type of systems is simply called a Hilbert space. It doesn't make Hilbert space, it is an infinite dimensional space. So in case if you try to understand what is exactly Hilbert space, what are the rules and regulations of Hilbert space, please go and watch Hilbert space video 1 to 6 classes. I mean 1 to I did almost 6 videos for only the design state of the system in quantum mechanics, how mathematically design the quantum state in quantum mechanics. So please go and watch those videos. Maybe you can get better idea what is quantum state or state of the system. Next thing, postulates. Postulate 2. Second postulate. Observables and operators. And operators. This is the second postulate of quantum mechanics. Especially these observable and operators. I did almost 7 seven classes, I mean, seven videos almost, maybe up to number 7 to 18th, last class, 18th, 18th. So this many classes I did, up to 7 to 8 classes. So all the videos are containing, revealing only the two information. So one is the what are the measurable quantities and what are the operators, what are the observable physical quantities in quantum mechanics. Okay, so therefore here I'm going to write these sentences. To every physically measurable quantity. Here I'm going to give one clarity, and that is physical measurable quantities. So we already discussed Hermitian operator already. So please go and watch that Hermitian. Then you can observe the what are the physical quantities. For your curiosity, I'm going to give one example here. Jx, Jy, Jz are physical measurable quantities, but J plus J minus are not physical observable quantities. Okay. So to every physical measurable quantity A to be called an observable or dynamical variables, there corresponds a linear Hermitian operator A cap whose eigenvalues from the complete basis. Basis. For example, so here I'm going to make one node observable quantities. Classical form, quantum mechanical form. Okay, the first one, coordinate. Generally, classical mechanics coordinates are designed by x comma y comma z. In quantum mechanical also x comma y comma z. Function of coordinate. Set of functions are there. For example, function of coordinates f of x comma y comma z. Here also function of coordinates are designed by f of x comma y comma z. The momentum component. Momentum component. Classical mechanics we can define these are sorry we can represented by the px, py, and pz, right? In quantum mechanical, there is an operator I h cross dou by dou x is a x component. So y component of momentum This is z component of the moment. So for example, energy is the energy E. Here we can express energy in terms of operator I h cross dou by dou t. Angular momentum L equal to R cross B, right? Minus I h cross. So this is our position into cross delta. Hamiltonian of the system. In classical mechanics, we know the H kinetic energy plus potential energy, right? So here we can express in terms of operators. Minus H cross square divided by 2m dou square divided by dou x square plus V. So this is the second postulate. Next, postulate 3. Third postulate. Measurements and eigenvalues of operator. Measurements and eigenvalues of operator. Or these can we can write another forms, eigenvalues and eigenfunctions of operators. Eigenfunctions of operator. For example, if an operator is A is applying on a wave function psi, it is produced by same wave function and multiplied by some constant value. So if you apply an operator on this quantum state, in case if you get same quantum state after applying operator and multiply by some constant value, this type of equation we can call here the eigenvalue equation. Or we can write this one, operator O is applying on a wave function psi, then we can get same wave function and multiply by some constant value. This is eigenvalue equation. Here A is the operator. Here A is operator, position operator, momentum operator, energy operators are there, orbital angular momentum operator. This uh, lambda called eigenvalue, eigenvalue. This wave function psi, eigenfunction. If there is a whole set of eigenfunctions, for example, uh, the situation is like this. If an operator A is applying on the nth quantum state of the system, then we can get here lambda n, a corresponding eigenfunction like this. So this is also called eigenvalue equation. So here lambda n associate with the eigenfunction. Okay, so then we can call this lambda spectrum eigenvalues, which means n is equal to 1, 2, 3, and so on. For example, We want to discuss one example here. For example, we know the plus and minus. These are general operators. We know plus, minus, and multiplication, divisions, right? And d by dx. This is also operated. And integration. This is also operated. So here I'm going to take one example. Here I'm taking operator d by dx and function, wave function, quantum function, e power kx, for example. So I'm going to, this is operator, this is wave function. So I'm going to apply d by dx, d by dx. So I'm going to design this quantum state like this. Okay, this is operator a. So in case if we apply this operator on this wave function d by dx, right, e power kx with respect to x, right, then I can get k e power kx. So in case if we try to observe this thing, d by dx e power kx, this is cat vector. If I apply this operator on this quantum state, here I got the same state vector, same wave function. There is no change in wave function. The extra thing here I got the k, right? So this is the best example to understand the eigenvalue equation. These look like a wave function psi, okay, not equal to lambda wave function psi. So after applying operator, we can get the extra constant value. This constant value or scalar value, we can call this one here eigenvalue. And this wave function we can call here the eigen function of the system. Okay. Next, fourth postulate. Postulate 4. Probabilistic outcome of measurements. Or expectation values. Expectation values. If a system is described by a normalized wave function psi, the expectation value of a measurement of an observable A is defined like this. A expectation value of A equal to wave function psi and A wave function psi. For example, if it is not normalized, then we can write like this. In case if it is not normalized, we already discussed what is normalized norm of this equation and probability of the function. Wave function, the expectation value we can write like this: wave function psi, operator, and wave function divided by wave function psi, wave function psi. Okay, if it is normalized, then we can write like this. Or in integration forms, this is very very important. It is useful solving problems. A wave function psi, the volume of the system, integral minus infinity to plus infinity psi star psi d top. Psi star psi, here the psi star psi. This is probability density. Okay. And this psi star psi d tau. This is probability. So probability density is always positive. Probability is there some values. Okay. Maybe you can get answer this probability and probability density difference by solving the problem. Then only you can understand, especially one dimensional, two dimensional problems. Next, fifth postulate. Postulate 5. Postulate 5. So you need to write these statements each and every time. Time evaluation of the system. The time evaluation of the state vector wave function psi of a system is governed by the time dependent Schrodinger wave equation. So that is a IH cross d by dt, the wave function psi. Here the wave function is time dependent. And H, this is Schrodinger time dependent wave equation, where is H is a Hamiltonian operator corresponding to the total energy of the system. Okay, so here I'm going to give the note. These are the 5 postulates. The first 4 describe the system at a given time, and the 5th postulate shows this describe the time evaluation of the system, evolves in the time. Okay, number A, the first 4 postulates describe the system at a given time. The 5th shows how this description evolves in time. Okay, so these are the basic postulates of quantum mechanics. Okay, first postulate is the state of the system, and second one and observable and operators. Third one is the measurements and eigenvalues of operators, or eigenvalues and eigenfunction of operators. Fourth one is probabilistic outcome of measurements or expectation value of expectation values. Fifth one is the time evaluation of the system. So these are the basic fundamental postulates